Hello, my name is Walker Anderson and this is my standing wave project. First I'm going to start with a definition of what a standing wave is, and a standing wave is just a pattern that results from the interference of two or more waves along the same medium. If you looked at it, it would kind of look like a double helix. You have one wave coming this way, you see the rarefaction and the compression, and then you see another wave that kind of mirrors it, where the compression's where the rarefaction is of the other wave. This is called a standing wave because if you look at a graphical representation of it, there are points along the wave that look like there's no movement, there's no displacement. Those points are called nodes. There are also antinodes that are positions along the medium that vibrate back and forth between a maximum upward displacement and a maximum downward displacement. So if you think about nodes and antinodes, nodes are where there's no movement and antinodes are where there's the most movement. The reason you don't want standing waves, say in a recording or when you're just listening, is because there's a tendency for sound cancellation, and of course when you're listening to something you want there to be as much sound that there actually is. And a way to prevent standing waves is to make sure that the wave is not hitting a right angle, because if the wave hits that right angle it'll come back, and because it's the same frequency there'll be a standing wave there. So now I'm going to measure this room, and hopefully we can see what frequency of a wave would be a standing wave in this room. Okay, so I just measured the width, I guess, of this room from this wall to this wall, and it measured at 136 inches. So if we want that in feet, it would be, it's about 11.33 feet. Okay, so now we're going to do these two walls. Come on. So the distance between these two walls is about 173 inches. So in feet, that would be roughly 14.41. And now we're going to do floor to the ceiling. Don't fall. There we go. Ow. Okay, so the distance between the floor and the ceiling is about 104 inches. So if I divide that, that comes to about 8.67 feet. Okay, so now that we have all of the measurements of between all of the walls, we're going to calculate what the frequency of a standing wave would be for all of them. And the formula we're going to use for that is wavelength equals frequency. Lambda equals velocity divided by the frequency. And since we already know what lambda and velocity is, and we're looking for the frequency, we're going to change the formula up to be frequency equals velocity divided by the wavelength. So this should give us the frequency we have. And we're going to say that velocity is 1,130 feet per second. Okay, so first I'm going to do these two walls, which measured out to be roughly 14.41 feet. So if we do 1130 divided by 14.41, that gives me 78.41 hertz. Hertz. Okay, so now for these two walls that measured 11.33 feet, take 1130 divided by 11.33, gives us 99.73. And now for the ceiling and the floor, which measured out to be about 8.67 feet, divided by 8.67, that would equal 130.3 hertz. Well, that's all the walls and all the calculations, so thank you.